Okay, hey, so this is chapter one. What I'm going to do is give you guys a couple different options of what to do with this. So I'm going to go through just the PowerPoint right now and record just my screen so you can see what I'm looking at and what I'm talking about. Um, I will also post the PowerPoint so that you can look through it on your own. And then as I get to some sections where we have to go over some problems or I have to write something down, I'm going to make separate videos for those and just upload them separately. So you'll have a couple different links. So if we get to a particular problem or something you need to go over more, you can just click on one of those videos and then watch one of those videos more. If you don't really want to hear what I have to say about the PowerPoint, you can always watch the PowerPoint on your own. But in any case, I'll kind of just voice some stuff over on this PowerPoint. This page, some of the stuff just has to do with coming to class, showing up on time, whatever, that kind of thing. Obviously, this stuff doesn't apply. I didn't remove it this time. I went over some of this in the preview video, whatever you want to call it, over the weekend. Like I was saying before, the main thing you need is practice, which is what it's saying here. You have to do just a million problems. That's the only way you're going to get better at this. If you have access to another person, like I said, if you're in a lab or something like that and you have a lab partner and you exchange numbers with them or whatever, if someone doesn't understand something and you have to explain it to them, that is definitely one of the best ways to learn, because you're never truly sure you understand something until you have to explain it to someone else. So that's a great thing to do. And like I said, I would get with your partners in your lab. If not, there are some people making some groups and stuff on Web Campus. I even have a guy in the other class who's making a Discord server, I guess, for the students. But you have quite a few options. Okay, so the homework. I will get the homework posted hopefully by tomorrow. I still have to go through the system and work out all the kinks. This just goes. I explained how the homework should work in the first video. This is just, a PowerPoint slide to show you what I said earlier. One of the other things on this is the having a homework notebook. If you have a specific homework notebook, that's a good idea. It's going to be, not as relevant to be sitting in class and taking notes and stuff like that. So, if you want to take notes while we're doing PowerPoints or whatever, that's fine. Having a separate homework book, with all the problems numbered and stuff and being able to go back to them and stuff, that's pretty useful. Okay, so the homework is there. Like I said, I'll get it posted. You'll be able to understand it hopefully here in the next day or two. And like I said, the practice is the most important. So the quizzes, I debated going back and forth on the quizzes. I'm still going to do the quizzes, I think. I don't think it'll be that bad. It's basically just going to be a timed version of the homework. And it should be fine. I don't think it'll be a big deal. Obviously, the stuff at the bottom of the page down here doesn't apply. The calculators and all that stuff, whatever you have at home, obviously is going to be used at your disposal. So use what you have, I guess. Again, any of these problems you're doing, you should be showing work for them. If we do the online quiz, which is built into the Wiley Online Plus, I don't think that's possible, so I'll have to look into that a little bit more. But the tests, for sure, I'll need to see some kind of work. We may just kind of glaze over it for the quizzes, but I'll work on that more this week. Okay, the tests, again, this is kind of like in-class stuff. It's not as relevant for the online semester. And then the grading breakdown is here. You can look at this. There's more on the syllabus. Like I said, I went through some of this in the first video. Okay, so chapter 1. Hopefully you guys have the book. Chapter 1 is basically just super basic. It's just about measuring things, how we came about measuring things, the standards in which we use to measure things, that kind of thing. So it just sets a basis that you can begin at. Here's some of the learning objectives, whatever. You have the SI system, SI units. That's all standard stuff that we use. Like if anybody ever asks you about that, you should know what they are. We'll go over changing units. Order of magnitude is one that's useful. Okay. So again, you have these standard definitions. You can look at these more on your own. The units at the bottom, talking about like mass, time, length, pressure, etc. These are the type of things that we need to measure and quantify. So let me see if there's anything really relevant on here that you can't. Anything you can go over on your own. I'm just gonna kind of skip over. I know you can read this on your own. There's no point in me reading a slide to you. I'm sure you're capable of that much. So yeah, you have some of the standards, some of where it began. They had like a lot of goofy methods originally of how to measure things, and you know what a standard foot was, and you know they had stones and rocks and whatever kept in museums for weights and all this stuff from a long time ago. So here were some of the examples. The way they used to define it 1 meter. And you can see like it's been a sort of a difficult struggle to try to make a universal language for all this stuff. Obviously, the rest of the world is pretty much using the metric system at this point. Like they all kind of got together and said, this is the easiest method we do things in. And then America's like, nah, we don't like science. We're going to do whatever we want to do. So yeah, so despite that fact, we aren't using any kind of American unit system in here. You're going to use standard metric system for pretty much all science and engineering related stuff. So yeah, so they had these different ways that they defined a meter. Like it's 1/10 millionth of the distance from the North Pole to the equator. They had like a bar they kept in France, you know, that was just constantly there. In case they forgot, they can measure it. But then, of course, they got to keep it under lock and key so it doesn't degrade in any way or change shape or size, corrode or anything. One of the other things, we don't get into that in here. If you are taking 182, you're going to get into that. The number 3, it's the wavelength of an emission line of krypton, I think that is. So basically, when you shine light through a gas of this stuff, you can see different colored lines. There's different wavelengths of light that come out of the gas. So this is actually how we tell what other stars are far away. We look at the emission lines and then we say, oh, this is comprised of this much hydrogen and this much helium. But it's a pretty exact thing. So they were using that to measure it. But the most recent way and the current way we use it is by looking at the path that light travels in a vacuum, which is very specific in a vacuum. So yeah, these are, again, they go over this more in the textbook. It's semi-important because you need to know where this stuff comes from and why we use it. So yeah, you can look at it on your own a little bit more in the book. Some of the what they call the International System of Units, the SI units. These are always the same. So, for instance, distance is in meters, right? So the SI unit is meters. Now, kilometers are also in the metric system, right? You got kilometers and meters. But if someone said, give me the SI units of that, you wouldn't put it in kilometers. It's always meters. Got it? So it's the same thing with the other units and what they refer to. Like, so seconds, it has to do with time. If anybody asks you for SI units in time, it's always seconds. That's just it. So you got to be very careful with how tests and stuff are worded, not only in this class but in future classes, because professors will like to kind of mess with you and word these things in such a way that you're not paying attention and you'll miss something. So if it says like, you know, whatever, give the answer in SI units and doesn't mention anything about it, and it gives it to you, you know, a submarine's underwater for 62 hours or something like that, that just means you have to convert it to seconds. And then you have some of these derived units down here. So these are based off SI units, if that makes sense. So if you break up the components of like a joule, you're getting kilograms, meters squared per second squared. So those are all in SI units, right? Kilograms, meters, seconds. So it's still using the SI system. So again, refer to your book more if you need to know more about that, if it doesn't make sense. At any time, if you have questions about things, obviously it's going to be difficult to have a long discussion. Like I said, I'm teaching 4 labs. If you come in at any of those times I'm teaching labs, I can talk to you about something a little bit more in length. If it's just a short question, like, you know, I don't understand what an SI unit is or whatever, you can email me. I know you don't know the times of the labs that I'm teaching, so I will post those and make an announcement about it later. Okay, so this is just, again, this has to do more with like scientific notation, that kind of thing. You get these prefixes that are added on, so you may be used to a lot of these because of computer data sizes these days. You get like kilobyte, megabyte, gigabyte. We're getting into terabytes now. I have a 2 terabyte hard drive beside me that is like, you know, smaller than like the palm of my hand. So we're definitely moving forward with this stuff. But you use it for anything, right? You use it, you can attach it to masses or times, anything that we measure. So here we have some more similar things, everything we talked about before, except now we're going to talk about order of magnitude. So if you wanted to say the order of magnitude is basically being specific about something. So if you said within an order of magnitude, right, and say something, you want to know a distance of something, the order of magnitude could be like 10 to 99. So if you were like, how many meters are we standing apart from each other within an order of magnitude, that creates like a huge error bar, right? You could be massively off by that, and it's still within an order of magnitude. We usually use these things for really large things, like, you know, distances in space, or, you know, the mass of planets or something like that. Then the numbers just get so large that the little pieces at the end of it become insignificant, right? It's just, it doesn't really matter if you have a couple extra numbers. Like we say the speed of light is 3 times 10 to the 8th. But you saw in that previous slide, it's, you know, it gets down to very exact numbers. But for most calculations, we just use 3 times 10 to the 8th meters per second. So again, the order of magnitude is just, it's a way of sort of approximating things usually. Physicists especially, and I imagine engineers would have to do this too. You may be asked, especially in interviews and stuff, you know, hey, we got the situation and we got these rough numbers. Give me a calculation off the top of your head, just within an order of magnitude, right? So that's basically saying, do it in your head roundabout as close as you can get, and then, you know, give us an answer. We understand it's not accurate. So usually it's used for that type of things. Conversion factors. So yeah, you'll have to use these conversion factors anytime. These are not necessarily things you have to memorize. It'll probably make your life easier if you memorize them. But if you if you don't have them memorized, like for instance on a test, if I give you a test and it says something like, you know, Bob is driving at 60 miles per hour, what is this in meters per second? I'm going to give you like a conversion from miles per hour somewhere in there, right? Because that's not a straight conversion. Um, if I said he's moving in kilometers per second, what is he moving in meters per second? That's something you can do without these conversions, right? You're changing the order of magnitude. You're changing how many where the decimal place goes, basically. This is pretty hard to explain without actually writing stuff on the board, I'm realizing, but hopefully you understand. A lot of this stuff's already basic. I'm sure you understand most of this before I even say it. But yeah, just make sure you know that the conversions are there. It lists some stuff in the slide. I'm using all kinds of hand gestures and stuff, and you can't see me, but yeah, they're saying by equating it to 1 and converting stuff, it's sort of standard algebraic stuff. Okay, so this method here, they're calling it a conversion factor. A lot of books, especially I believe in chemistry, they're going to call this like dimensional analysis. So when you go to convert one thing to another, this is dimensional analysis. Once you got the method down, it's very simple. It's not anything you have to like really memorize. Once you understand the mechanics of it, you can do it to anything. So you don't need to constantly like force yourself to memorize how to do this or something like that. And this one I'll do a separate video on. So if you need that, you can pause this now and go to that video. Okay, the scientific notation. Basically, this is how we shorten things. When you write in scientific notation, one, you're going to say if you're in the lab, you're taking data, you're going to round something down to the amount of significant figures you need and then write it in scientific notation. Right? So it's not getting to significant figures yet, but there are 3 significant figures in this number right here. And then they are placed right here. So we keep that data. And then 10 to the 9th is adequate to replace the rest of this. Try not to get too much into scientific notation or in significant figures until we get to that slide. But the 10 to the 9th, so basically you're moving the decimal point this way, right? Because the decimal point should be right here. So you're moving it to the left, and you should be moving it 9 spaces. That's how you're counting that. So anytime you move to the left, basically the number is increasing and positive. So the number below is a small decimal point, right? It's a small number. So if we go to put this in scientific notation, we have to move to the right now. So that means the number goes down. So if you think of it as a, what is this stupid thing? Okay, so yeah, so if you think of this as like, if you think of a number line, it actually works backwards. So if this was a positive negative number line, and again, this is difficult to explain without being able to draw it. But if I move to the right on a number line, those numbers get increasingly positive, right? They get larger in a positive manner. If I move to the left, eventually I get to 0, and then they become negative. So it actually works the opposite of that, right? So if I have to move to the right, this number becomes more negative. It's like a reverse number line. If I have to move to the left, then the number goes up. So that might be an easy way to remember it. I'm not sure. Or this is again something you probably should have been doing in high school. You should be familiar with it. So again, refer to the textbook more if you need more on that. Maybe I'll put in some more in the video for this when I have a whiteboard in front of me. Okay, so what we call sig figs, that's just significant figures for short. There's 2 different methods of doing the sig figs, and there's just a bunch of words on the screen, but there's basically multiplication and division. You use one method to do sig figs, and then addition and subtraction, you use a different method. And there, if you need to know about that, I'll try to do a short video on it, and add it to where I add the rest of this stuff. But there's definitely tons of videos on the internet and YouTube and everything else on this. It's pretty standard procedure for K through 12 stuff. Okay. Some of the important things to remember about the sig figs are like the leading zeros. So you have to ask yourself how much of this has information in it. And that's what we're saying here. And when you give a number like this, the 6.20, that is giving you information. It's saying how precise the measurement was in the beginning. If this thing had like 72 zeros after it, that means someone measured whatever this was to a very precise degree. They had some kind of amazing instrument that left no room for interpretation, and all these zeros mean that number it's on point, right? The numbers in front don't give us any information. So when we move this decimal point over, we have that information contained still right here. And it's not adding anything else to this. So when you're in the lab, again, these numbers aren't necessarily giving you information about what you did, but the zeros afterwards are going to. So try to keep that in mind when you do these. Okay, so this they call it chain link conversions, but a lot of people call it dimensional analysis. It's the same thing. Measures of motion. So just like defining time. So rotation of the Earth, obviously, is it, one full rotation of the Earth is a day. You have the quartz vibrations and atomic clocks. And then, they have atomic clocks you can access nationally to set your watch to it to make sure it's accurate, because every watch that's made is not exactly the same. So they try to have this, again, standard way of making sure they're all the same. So you have, again, at the bottom, this is the current method of how we do. They're doing the 1 second is the time taken by this many oscillations of light of a specific wavelength, and it's of a cesium-133 atom. So yeah, great stuff. I'm sure you'll remember that for the rest of your life. Super interesting. Okay, so time. There's just some random times here to give you an idea. You can kind of put it in scientific notation here. Time between human heartbeats, etc. The Planck time. Oh, they really like this, don't they? This is the earliest time after the Big Bang in which the laws of physics as we know can be applied. So, very short amount of time, right? So, yeah, you have some of the larger numbers, age of the universe, lifetime of a proton, if you don't destroy it or turn it into something else. I guess I shouldn't say destroy, if it gets changed into something else. Okay, so that gives you just some, again, combinations of scientific notation, orders of magnitude, that kind of thing. So this is just showing the rotation and then the atomic clocks. This is just some more information you can look at on your own. I don't think I'm going to add anything too significant to this that the book didn't already add. Okay, moving on to mass. We get back to the standard kilogram. So again, they keep a cylinder that is exactly the measurement of a kilogram, 2.204622622 whatever pounds. That's your conversion. So that's kept in France. It's always there, and again, they keep these things sealed up. They don't want like dust and debris falling on it or corroding and oxidizing with the atmosphere and changing what it actually weighs. So Then you have the atomic mass unit, the AMU, right? You're probably familiar with these because of the periodic table of elements. Might have learned this in chemistry, or maybe you will if you take it. But then it's just they take one atom of carbon 12, and I think it's just 1/12 of that. Which, yeah, so they're saying 12 units. So, and then you can use these for the rest of everything. So, okay, so some more orders of magnitude, just comparing different things. The interesting thing here maybe is that you ask, how do we know the masses of these things? A lot of these things are just by rotation speeds. So we measure, like say a galaxy, our galaxy, we measure how fast it rotates. And then just using like basic Newton's laws, we can figure out the speed in which it's rotating, and you can ultimately figure out the mass from it. One of the problems that astrophysicists have is the problem of missing matter. So they look for how much something weighs, like a galaxy, and they look at the mass, and then they calculate it, and they say it should be this much, and then through other means it doesn't match. So this is how they came about of having and sort of creating dark matter. So they say we're missing all this mass, so it must be in the form of dark matter. It's out there, we just can't see it, but it must exist because Newton laws work on these large scales. So, but that's a whole another can of worms. Basically, you can look into that too if you want. Okay, so they were talking about density here. So it's just a mass per some unit volume. And then they have some examples down here. You can calculate it. This is one of those things. So this symbol here is not actually P. You should get familiar with Greek letters. You're going to use them quite a bit. Even for engineering stuff, you're going to use them here and there. Probably not as much in physics. We used all the letters and then ran out of the letters, and then used all the Greek letters and ran out of those too. So it's a big pain. So this is actually called rho, and this is the symbol for rho. Basically, it looks like a P. It just doesn't have this little piece that goes over here. And so also when you start to take notes, write formulas, do problems, you have to be very careful with your handwriting. Way back in the day when I was doing this as an undergrad, I had to write very slowly because my handwriting was terrible and it was very sloppy. And I had to learn to write things very accurately because I would confuse it as something else later, or I don't know, think it was something completely different and mess it up. So it's very important to differentiate between these letters and to get them correct and to be able to read your own handwriting. Okay, so I believe that is most of the PowerPoint. And then we're going to go into some problem solving here. I'll back up. So this is going to get, obviously I can't do the problem solving in front of you. I'm going to have to do a separate video for that just to run you through a problem and to show you. But for right now, it's just words. So yeah, here's a bunch of words, word problems. You know what they are. You know what they look like. They have a bunch of stuff in them. Again, you can read this on your own. There's nothing enlightening in there. This is another part of the dimensional analysis. This is actually extremely important and extremely useful, so you should pay attention to this part right here. So we have length. I'm pointing at things, you can't see it. We have like length, for instance, here, and then you have a velocity, which broken down into its units should be some length per some time, right? If we use standard units, then this is meters per second. So it's velocity, meters per second. So when you go to write something out and you're doing a problem, if you, especially in the beginning, if you're not confident in what you're doing or you repeatedly do problems and they're wrong, one of the things you can do is carry out the units through the whole problem. So if you're given some mass, say it says the velocity equals 5 meters per second. Instead of just writing 5 in for this v, you could write 5 m over s, right? And you keep that the whole time. And then you write time here. Well, time is seconds squared, right? So all of a sudden, this second gets canceled and you have a second up here, right? So it helps you change what you're doing, and it helps you keep track of what you're doing. So you're saying they're basically saying, like, does this work out, right? So when you do this problem, you're looking for some length, and you say, okay, I think this was the equation. I don't know. I'm just guessing off the top of my head. I'm taking a test or whatever. And you go to do it, and you put in meters per second, right? You put, okay, this is seconds, so that's second squared, so that cancels one in the bottom, right? So now you have meters times second, which is what they're showing here. This is meters times seconds. So that does not equal meters. So basically, you have screwed up this equation, right? You basically need to get rid of the squared part, which is then what they do, right? You get rid of the squared part. Now it's meters per second times seconds. So the seconds cancel. And again, I can do this in a video so I can show you more visually. I know this has got to be a headache just listening to me do this. And then we have problems. So this is problem 7. Wow, and it is huge and the resolution's horrible. But again, I will make a separate video for this and go over with you. I will do it for you and then show you some of the advice I can give you just right off the bat when you're doing any of these word problems, especially in the 150 series classes. It's mostly biology students. They all freak out because they don't like math, they don't like physics, they don't like any of it, and they always say, I'm terrible at word problems. You have to just get over that. Physics is all word problems. I just, it's so weird. I haven't heard the term word problems in I don't know, decades probably. But the thing is, it's just a bunch of worthless information that's kind of painting a scene, and sometimes it tricks you. Almost never does it help you. You just need to pull out the specific information you need every single time. Hydraulic engineers in the United States, all this is worthless. You can just get rid of it. You don't need that information. It's not relevant. Saying they use a unit of volume of water, the acre foot. Again, this is all irrelevant. It's just there to confuse you. And then they define what it is. Will cover 1 acre of land to the depth of 1 foot. So this is probably a piece of information, if you keep going, that you're going to need to use. Severe thunderstorm dumped 2 inches of rain. A severe thunderstorm, worthless. All you need to know is that we now have 2 inches of rain in 30 minutes. On a town of this, again, the town doesn't matter. You have an area of 26 kilometers squared. So if you get rid of most of these words, it's actually very short, and it's more or less like a regular problem. Some of the other word problems, as you go on, they get more difficult and you have to kind of pay attention to them, but the words can throw you off a lot of times. So I would suggest just pulling out the information you need right away before you get lost in whatever they're talking about, because they're trying to confuse you by talking about an acre foot and all this stuff that nobody ever uses or has heard of. Except apparently hydraulic engineers, which I am not. So whatever, I'll go through this problem in a bit. Like I said, you can go to the separate video. Same deal here. Antarctica is roughly a semicircle. So basically, you don't need any of the first part. All you can say is we're going to do something with a semicircle, right? Doesn't matter that it's ice or whatever. But again, I'll do this problem. We'll go over it. And then same thing here. It's just iron has this density, and talking about the atoms of it, I'll go over this problem too. So that's pretty much it. Here's what we did. This typical summary stuff, what you should know. Look at this on your own. Go over it. And that's pretty much it. I'm not trying to make these videos super long. Just give you the information, and then now I'll make the other videos on how to actually do these problems, and then you can access those. So like I said, if you have any problems, email me.